Hello everyone, my name is Pandya and I'm going to be presenting the AtlasNet paper. So talking about the motivation and the main problem, this paper talks about generating high resolution 3D shapes which still remains an open challenge. And the way this paper works is that you give a 2D image or a 3D point cloud as an input, and then it works on the encoder decoder mechanism, and the paper mainly focuses on the decoder part, such that using one of the encoder techniques, depending upon the type of input, you can generate an output mesh from it. And the Atlas part in this generation helps in sort of putting together the entire mesh such that you can get a high textured output, and you can also 3D print it. So the importance is that basically it forms a basis for many applications in three-dimensional space. So you can use it for auto-encoding shapes, for single view reconstruction, for morphing, and as well as for parametrization. The parametrization part is still an open challenge because it is a very difficult geometrical problem where you have to map points from a 2D space into a 3D space. The issues with the current approaches are memory issues with certain representations like voxel grids, as well as resolution mesh formation and parametrization of meshes. Like I said, it's still an open problem. Voxel grid based methods are memory intensive. Plus, there are certain methods which don't really provide much surface connectivity. So there are tessellation problems where when you have complex shapes, it becomes difficult to generate the entire shape through tessellation of polygonal planes. And then also it is difficult to automatically estimate correspondence between training shapes and base meshes, especially for the ones that uh, don't really have a lot of similarity. Uh, in other words, heterogeneous data sets. So contributions. So the main contribution of this paper is to formulate a method to generate the surface of 3D shapes. Of course, as like I said before, it is a very important and a hard problem. Key issue of the prior work is low precision meshes formation and memory and tessellation issues. And the key insight of this paper is that in the decoder part, you have to sample points from a 2D space. So let's say a unit square, and then you use that to generate points in 3D space, and then use one of the surface reconstruction techniques to generate patches to form the entire surface of the 3D shape. And the result of this insight was that the generated surface had a better precision mesh formation, and it didn't really cause any memory issues. Talking about the background, like I said before, voxel grids and the hierarchical surface prediction methods, they are usually, so the voxel grids suffer from the problem of memory issues, while the hierarchical surface prediction methods, they are pretty much complicated and memory intensive as well. And there is also this point set gen method, which can help you in generating surface using point clouds. But as you can see, the surface is very bubbly and you don't really have a textured output. So it's simply yet unstructured. And like I said, this paper focuses on the decoder part. So for the encoder part, you can use different pre-existing methods. So if you have a 2D image as an input, you can use the ResNet encoder, which is a type of CNN with skip connections, which helps in generalization. And then if you have a 3D point cloud as input, you can use PointNet encoders, which are basically a layer of, which are basically a series of multi-layer perceptrons. Uh, and chamfer distance is one of the metrics which is used for comparison of the output. And this is a very intuitive video which you can watch later. Talking about the problem setting, so the multi-layer perceptron with rectified linear units are used as the functions which are used to sort of map the points from a 2D space to a 3D space. And generally a variety of these multi-layer perceptrons are used to generate different patches to better cover the surface. So what this does is that you have a latent shape representation, which is a vector produced by the encoder. You concatenate the points which are sampled from a 2D plane, like a unit square. You concatenate these two and pass it into the multi-layer perceptron, which generates the points in 3D space. And you get a patch in 3D space. And yeah, the goal is to produce a 3D mesh output. And the way this works is that it works by optimizing the chamfer distance metric and the set of generated points in 3D space are compared with the original output during the training phase to sort of optimize the parameters of the multilayer perceptron. This is a very intuitive image which the author has used. So for example, if you just use one multilayer perceptron, you can see that it is just using one patch to cover the entire surface, which is not really a good output. But when you use multiple patches, you can see that it covers the surface in a better way. So use multi-layer perceptrons, multiple multi-layer perceptrons. Talking about the experimental results, so this was trained on the ShapeNet core dataset, and chamfer distance metric and the metro criteria were used primarily to see how they compare quantitatively. So it compares you to the points baseline where points are not sampled from a 2D space. They are just the points in the 2D space are sort of mapped into a 3D surface without using any sampling method. And as you can see that as you increase the number of patches, the chamfer distance as well as the metro criteria decrease, which produces better quality meshes. However, if you overdo it, then it can result in certain problems, which I will talk about later. So these are the meshes which are produced. And as you can see that as you increase the number of patches, the surface gets better quality and high precision meshes are formed. One good thing about this approach is that it generalizes well to unseen data. So if you have trained, let's say on a chairs data set, then not only can you improve the precision using that, but even if you don't train it on a chair data set, then it can generalize well. So it generalizes well on unseen data. These are the results from single view reconstruction. So as you can see, compared to the different approaches, the ones formed with the help of AtlasNet are sort of better in quality. So the 3D R2N2 produces a really coarse, untextured output, whereas the other ones, like for example, the point set gen method just produces point clouds, which don't really help with surface generation. And the hierarchical surface prediction also generates meshes, but they are not that accurate. Talking about the applications, so it can be used for shape interpolation, where you convert one shape into the other just by changing the orientation of the points. Shape correspondences help in sort of providing a semantic meaning to these shapes. So for example, all of the shapes which are used for sitting, for example, a chair or sofa, they are all corresponding to each other. And then mesh parametrization. So this is essentially used for gaming industries where you create textured outputs, where you create a textured mesh and then apply it to a 3D surface. It is also used for super resolution, where you have where you typically have less number of points in the 3D space, but you're still able to generate high quality meshes from it. So whether you have 2500 points or 250 points in 3D space, still the difference in quality is not that much. So the following conclusions can be drawn. So it's not as memory intensive as the other approaches like voxel grids. It finds application in various domains like shape interpolation and correspondence. The resolution and precision can be controlled depending upon the number of patches you select, and that is why this is a very flexible approach. And it also has good generalization capabilities, so it performs well on unseen 3D shapes. And yeah, these results are fully supported qualitatively and quantitatively. So talking about two main limitations. So when there are less number of learned parameterization, it sort of distorts the triangles and creates larger triangles, which sort of fill these open spaces. And that is why you get some coverage in the undesired portions as well. And then talking about the second limitation. So if you overdo the number of patches, then they can sort of overlap and the mesh is not stitched together properly. So that was the paper. And one of the questions that was asked, which really drew my attention, was can we determine the optimum number of patches? I searched a lot for it, but I couldn't find any substantial evidence to back that claim. And that is why what I think can be done is that you can use an algorithmic trial and error method where you can train it for different number of patches, and then using the metro criteria, you can sort of decide which one to choose. So iteratively, you train it over multiple number of patches, then you compare them using the metro criteria, and then depending on the one that is the lowest value, you can select that. But however, that is very expensive to train and not computationally efficient. So that is it, and thank you for listening.